Hello everybody and welcome to a new Back to Basics video. Today we're going to have a look at Zener Diodes. These are actually pretty neat little pieces of technology, and they're exceedingly useful for a bunch of different purposes. So this video is going to be a little bit longer because I'm going to talk a little bit more about what Zener Diodes actually do and how they're utilized. But basically, a Zener diode is a diode that, and that's what the symbol looks like. If you put voltage in this direction on it, it acts just like a normal diode, and you get a forward voltage drop of 0.7 volts, or thereabouts. Now, the really cool part is when you take a Zener diode and you put voltage on it in this direction. So we'll put the positive here and the negative here. Now, for your normal everyday diodes, say a 1N4007, nothing's going to happen until you hit about 1,000 volts. Then you have something called Avalanche Breakdown, at which point the diode will start conducting, reverse biased, and in most cases, diodes will start to fail. That's why they call it avalanche breakdown. The materials actually start to fall apart. But Zener diodes are actually designed to operate in this manner. Now, depending on how the doping is done and the construction of the Zener diode is done, this voltage can be anywhere from I think the minimum is about 0.5 volts, all the way up to, several hundreds of volts, I think. Pardon me. Yeah, the highest Zener voltage is 200 volts. Pardon me. So, why is this important? Well, they can be used in voltage regulators, AC clippers, voltage, what was that term? Voltage shifting, and all sorts of things. And we'll talk about those briefly in a little bit here. But first we're going to talk about how Zener diodes are constructed, and it's ridiculously complicated. So, we're going to start with a lightly doped section here of p-type material. So actually I need to move that out of the way. We'll put that over here. So lightly doped p material, so p minus. And then here is going to be a heavily doped section of n material, so n plus. And then oh boy. I'm trying to follow off of a diagram here. And I didn't quite make this big enough. Bear with me here. So we're going to bring this out just a little bit more. There we go. And there's that. Alright, so this section is going to be lightly doped N material. And then we're going to have some kind of weird sections here, like this, and the same thing on this side, of P plus material, so heavily doped P material. P minus. That's N minus. And then there's going to be a section like this. Like I said, these Zener diodes are really complicated. Well, modern ones are. Okay. And this is going to be P minus material. And then, again, there's going to be another one of these things of P plus material. And then the... Oh bugger. Okay, so P plus, and then there's just a little tiny nubbin here of N plus right here. I really need sharper markers. And then you have the electrodes coming out of those 2 points there. So that's what a modern Zener diode looks like on the inside, the construction. Now, early Zener diodes were just your standard we'll do it with colors this time. I should have been doing it with colors in the first place. There we go. Standard heavily doped. So this entire section was N plus, and this entire section was P plus material. But then they discovered new, better ways to build Zener diodes and came up with that really ridiculously complicated structure. Now, the reason why it's done this way is that the depletion regions tend to be very small. Whereas in a standard diode, the depletion region will be very large and harder to overcome. The depletion region in a Zener diode is very small and easier to overcome. And there are two factors that affect current flow through a Zener diode. One is the Zener Effect. And the Zener Effect basically describes a quantum tunneling effect. Now, I don't want to get into quantum physics or anything, so I'll basically say that you're going to have an electron coming along, and he's going to get to about here, and he'll say, well, I can't go through there because there's a depletion region. So he'll just kind of blip and reappear over here and continue. Once the potential reaches the appropriate value for that quantum tunneling effect to kick in. Now, the quantum tunneling Zener effect only really happens in diodes below 5.6 volts. I wasn't able to really find a back to basics video style answer for why it's 5.6 volts. So we'll just say that's the magic number of quantum tunneling. Now, once you exceed 5.6 volts, it falls down more into the Avalanche Breakdown effect for current through a diode. But again, Zener diodes are built to operate in the Avalanche Breakdown region. So let's have a quick look at the current characteristics of the Zener diode. So on this axis we're going to have current, and on this axis we're going to have voltage, and this will be plus and this will be minus. So for your typical diode, you're going to have very little current flow going along, and then it's going to hit the 0.7 volts, and then the current will climb dramatically. And that's your normal diode. Now, going in the opposite direction, you'll be coming along, there will be very little reverse current, and then all of a sudden, like for 1N4007, so let's say this is 1000 volts, it just kind of goes bonk. And they call that the knee. It's a very sharp drop off, there's a huge current flow, and that's why there's a breakdown. Now, for Zener diodes, those knees, let's say you have a 60 volt Zener, that knee will come along and it'll drop off at 60 volts. And then, of course, you'll get a drop off at, 5.1 or so on. So when you hear the term knee voltage, that's what they're talking about. It's the point at which the diode will start conducting in reverse biased. That's reverse bias. Oop, let's move that up. And of course forward bias over here. So that's a little bit of the science and math and a little bit of a graph there with what Zener diodes do. Now let's have a quick look at some circuits involving Zener diodes. Now you can make a very primitive voltage regulator with the Zener diode, and this is actually done in a lot of low voltage situations. And then we're going to bring the Zener diode like that. And then you're going to have your load out here. And this will be voltage. So basically what happens here is you're going to have the voltage, and as the voltage rises, when it reaches the voltage of the Zener diode, it will start conducting in this direction. And being as a Zener operating in its reverse biased condition has a very low impedance, the voltage here will be equal to the voltage of the Zener diode, because it's of course in parallel. There are disadvantages to this because you do have to regulate the amount of current going through a Zener diode. They can't generally handle a great deal of current. So it has to be a very low current circuit that you're using this regulator for. The other disadvantage to this is that if your voltage here is less than the Zener voltage, that voltage will appear here. So it better not be a circuit that will malfunction or be damaged. But, well, I guess it couldn't really be damaged by having too little voltage, but it may misbehave. So that's one use for a Zener diode. I made once a very primitive multimeter with a series of Zener diodes. And basically, the way I accomplished that was by having a Zener diode in reverse bias, and then followed by an LED that was forward biased. And this one was actually demonstrated on my channel. I guess I'll put a link over here. So, light emitting diode, and so on and so forth. And you do this with different values of Zener diodes so that as the voltage increases, you can tell I'm starting to get bored drawing there because it gets worse and worse and messier. Anyway, as the voltage increases, more LEDs will light up. So it doesn't really matter what order you put them in, but what I would do is I'd put my low voltage ones here and the higher voltage ones there, and as the voltage increases, the LEDs will light up, blink, 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 one after another. And of course the voltage that will be described here, let's say this is a 5.1 volt Zener, the voltage to get this to illuminate here will be 5.1 volts plus the forward voltage of the LED, which is, say, 3 volts, if it's like a blue LED. So that would be about 8 volts at that point. So that's another interesting thing that you can do with Zeners. It's not a particularly practical way of doing it, but if you need a quick and dirty way of visualizing voltage in a circuit, it's a good way of doing it. Anyway, so let's also talk about a waveform clipper. I'm trying to get into the habit of using the European style of resistor here. So a waveform clipper is going to have two Zener diodes looking at each other like so. And then there'll be an output. And this is used with AC. So let's say you put in a sine wave on this side of it. Your output is going to look like this. It's going to come up, flatten off, go back down, flatten off, and then come back up. And of course, if you put a sawtooth wave in, it'll look like this. And so on and so forth. Basically, it will clip the top of the waveform off at whatever the voltage of the Zener is, plus the voltage, the forward voltage of the other Zener. Zener. I actually haven't gotten a solid answer on the pronunciation of that, so I will probably flip between Zener and Zener randomly. So another example of what you can do is a voltage shifter. A voltage shifter looks like this. That is a terrible Zener diode drawing. Oh well. Now you'll notice that the positions of these components are backwards from the voltage regulator that we previously had. So basically what happens here is if you have voltage and it's increasing linearly or non-linearly, it doesn't really matter. So I got voltage on this graph and time on this graph. What you're going to get on the output is a slightly displaced voltage increase. And basically, if you were to draw a box with the previous waveform, like so, that's kind of messy. This point here will be the voltage of the Zener. So you can really manipulate the way electricity moves with a Zener diode, in a lot more different ways than you can with just standard silicon or germanium diodes, or even Schottky diodes. Anyway, I think that about covers Zener diodes. If you have any questions, please feel free to ask in the comments below. If you haven't already, consider clicking here to subscribe. Right over here will be a video that YouTube thinks you will find interesting based on your watching habits. Right over here will be the Back to Basics playlist. And right here will be the Patreon link, which you can use to help support my channel and further videos like this one. Thanks so much for joining me, and we'll see you next week. Bye-bye.